I just put that. And then when she's doing the slides, I just zoom in on the slide. That's it. That's it, that was pretty simple. I'm gonna write this.
You got the one slide.
Huh? No, sorry, no. Light work, light work. Now my Logan is like working right now. Woo! Working on my type 2, type A, type 1, type X. You know what I'm saying? These are my 8 CPPCs system.
Larry. He's here?
I saw him in the park.
Jalen's forgotten that he's in this class.
You might want to make sure he
I
drops.
want to remind him to check that. Because
You sure? Biology? It's not even is it really? Shout out to follow me at
all right. We have one slide to do, and then we'll start the review. All right. So we've been through the respiratory system, and we want to look at what happens in the respiratory system when we start to exercise. All right, and it's important to think about the reason we do these two chapters together is because they go hand in hand. Okay, if the goal is to get more oxygen to the muscles, then we're going to see a change in ventilation, but we also see a change in blood flow, increase in blood flow. So we're going to look specifically at the respiratory system because we looked at the changes in blood flow in chapter 6. All right, but they go hand in hand. I can't have one without the other because the overall job would not get finished. Okay? All right, so when we're working submaximally, so if I go for a bike ride and I get to 15 mile an hour and that's where I'm running, or I'm running on the treadmill at 6 mile an hour, right? I'm doing something at a submaximal level. Then we see these 3 phases within ventilation. And this isn't very clear up here, but it is in your book. So that diagram is there. All right, so what we get is phase 1, and because your cortex is responsible for the initial increase in ventilation when I start exercising, you know you're going to exercise. And so sometimes we see a slight increase in ventilation before you start to exercise. Just a little one, just to start getting you ready. And then once you start the exercise session, we see a very rapid increase in ventilation. All right? So here's my start of exercise. When I'm at rest, ventilation is mostly controlled by the blood levels of carbon dioxide. All right? So at rest, chemoreceptors, everything are just keeping an eye on that carbon dioxide and not producing a lot of carbon dioxide at rest, because we get that when we start to make a lot of ATP. Right? So it's relatively stable, and then we see a sudden change. Right? So we get this rapid rise in ventilation. We start breathing much deeper, and then if we need to, we'll start to breathe more quickly as well. Right? And we rise up to the start of steady state. So phase 2 is that transition here from rising to steady state. That means I'm breathing enough to meet the oxygen requirements for the exercise level that I'm working at. Right? So steady state, we use steady state, that term, for heart rate, we use it for ventilation. Right? Any time where I've got exactly what I need to do the workload that I'm doing. So we flatline here, this is submaximal, remember? Right? So I'm breathing fast enough or deep enough to get the amount of oxygen that I need. And then in phase 3, we see the cortex and the chemoreceptors working together, especially the chemoreceptors, to be fine-tuning here, right? They're fine-tuning breathing as you're riding your bike, running. And then we stop exercising. And as soon as we stop exercising, the motor cortex stops sending a signal, because you don't need that level of breathing anymore. But we don't remember our EPOC that we talked about ages ago now. Right? Excess post-exercise oxygen consumption. When I stop exercising, yes, we see a very rapid, immediate drop in ventilation, because I don't need to be breathing that hard. Okay? As soon as I stop, but I don't go back to resting level for a while. It takes a little while to get back to resting ventilation because of EPOC. Right? So this part of the curve, this kind of less steep area of the curve before we get back to resting level, is going on during that EPOC phase that we talked about before spring break. Right? If what I'm doing is closer to maximal exercise, so if instead of going for a bike ride, right, I go and do some sprints or some hill runs, or I go lift, right? If the work that I'm doing is anaerobic, if it's nearer to maximal levels, so high intensity, then we see this pattern occur initially from race to exercise. But instead of getting this plateau, we get an ongoing rise that becomes unbalanced a little bit. All right? So what happens is, as intensity gets higher and higher, we start to breathe faster than you would think you would need to breathe for that workload. So the curve gets a little unbalanced. And we have to, that response occurs because we change acidity levels, right? If I'm working at high intensity, I'm probably using glycolysis and or ATP-PC system, and I'm producing an acidic environment. Okay? So the pH changes, that stimulates the chemoreceptors to make you breathe harder. Okay? Temperature goes up, and that stimulates an increase in ventilation. Norepinephrine levels are higher as you work at higher intensity, and they stimulate ventilation as well. Right? So there's several different factors that create this different curve if the work is of higher intensity. Now the relationship between the curve, between our breathing and the levels of acidity is something that we touched upon in lab. Those of you that aren't in lab now have to go back and look at your lab books. But a little while ago you calculated ventilatory threshold in lab. Ventilatory threshold is an estimate of lactate threshold because it occurs, this imbalance in breathing occurs in a large part in response to the levels of acidity in the bloodstream. Okay, so as the acid levels go up, I start breathing faster. So I'm able to use breathing faster as a measure of lactate threshold, as an estimate, which is great because actually measuring lactate threshold involves a blood draw, which is a pain in the neck, because you have to have all kinds of permissions, you have to have special equipment, you've got to spend money on rubber gloves, you've got to do all this stuff if you're going to take a blood draw. Instead of using a blood draw, I can do a non-invasive estimate of lactate threshold by using ventilatory threshold. Right? So they've got a nice section on that in the book, and you've also got your quick summary version in your workbook for lab about ventilatory threshold. All right, they do have a whole brand new section in this version of the textbook just after they've introduced ventilatory threshold. I would not spend a lot of time in that section. It's too complicated. It's more than we need. All right? Okay, so that's what happens then. That's the response in the system when I start to exercise. What happens if I look at a chronic picture? Do we see changes in the system? So at sea level, right, if I'm at sea level and I'm healthy, then typically breathing isn't a limiting factor if I'm doing low to moderate level exercise. All right? It might become more of a limiting factor if I'm working at high intensity, or if I'm not healthy. So if I have bronchitis, or if I have asthma, or I have any kind of issues with bronchodilation, then it would be a different picture. But if we're looking at a healthy person, at sea level, breathing generally is not something that stops you exercising. Right? It doesn't impact how long you can exercise for. Respiratory muscles, so remember we said that the diaphragm and muscles around the rib cage, they're all highly oxidative. They're very, very good at using oxygen. They work aerobically. Right? And that means that they're relatively fatigue resistant. So unless I'm working at very high intensity, or as we go up the mountain, as we get higher in altitude, then generally they don't get fatigued very much, all right, for most people. They are a muscle like the heart and skeletal muscles. So we do see some training effects in the respiratory system. All right, so people who train endurance events, their diaphragm and their other respiratory muscles become better at oxidative phosphorylation. So we see changes in the enzymes, they become more efficient at using oxygen. If you do weight training, or if you're a manual laborer and you're picking things up and moving things around a lot, so you're not doing endurance work, but you're doing something that's high intensity, anaerobic type work, then we see changes in the diaphragm. The diaphragm becomes stronger and gets a little bit thicker, right, in response to the training stimulus. So we do see some training effects within the muscles of the respiratory system, right? But as I say, for most people, most of the time, breathing doesn't impact performance. Right? It's a different picture as we go up in altitude. It's a different picture if you're working with someone who has issues with bronchodilation. Question? No questions? I am good. All right. Okay. So, get into your teams. Here we go. Number 3. Who's going to come out on top today?
Scotty, too high. Let's go, Scott. MVP. Oh, no, Commissioner.
We've got 25 minutes to work on this.
You live here. You live More brain.
Let's go back to the office and show you how to upload it. Just place like a meeting so they can record it online.
Show value.
It's not like.